This is Lecture 3, Part 1 for Radiochemistry 702. This lecture will cover nuclear reactions. We'll go over some notation, energetics of reactions, the type of reactions, some information on cross-sections, reaction observables, what's evaluated with reactions, and then different types of reactions, scattering, direct reactions, compound nucleus. And finally, we'll end with an example related to formation of nuclides in stellar systems, so nucleosynthesis. This first part of the lecture will cover up to cross-sections. Nuclear reactions can be defined as any sort of reaction between a particle and a nucleus. The particles can be another nucleus, a subatomic particle, an electron, a photon, and it's used to produce or react with nuclei. Nuclear reactions have certain properties, they're on short time frames, and there's energetics involved in the reactions that can be evaluated. The first nuclear reaction was described by Rutherford, and what reaction was this? Well, it's the one that's listed at the bottom of the page, simply an alpha particle interacting with air. Now there are a number of terms that are conserved during nuclear reactions that can be used to evaluate the behavior. And these terms are listed here. They include number of nucleons, except if you have annihilation reactions, charge, mass, momentum, angular momentum, parity, etc. And just as we discussed before, we can evaluate the energy of the reaction, a Q value for a reaction. Positive Q values correspond to energy release, and negative ones correspond to energy absorption. And Q values are given in terms per nucleus transformed, so we're evaluating the energy at a single atom level. Now, one way that we're going to discuss on how to write these reactions, you may see the reactions is listed here, where you have a target, a projectile, a product, and another product. So this reaction above can also be written as a shorthand below. Important aspects of nuclear reactions are their energetics, and these energetics are extremely large compared to chemical reactions. As an example, let's look at the reaction of the alpha particle on nitrogen 14. The Q value is listed here, about -1 MeV. Remember that this is a per atom basis, so let's make it a per molar basis. We use the conversion factor of 1 eV is equal to 1.6 times 10 to the minus 19 joule. If I have 1.193 MeV, multiply that by Avogadro's number, I get the value listed here. So it's -7 times 10 to the 23rd MeV per mole. Convert that to eV per mole, it's -7.18 times 10 to the minus 29 eV per mole. Convert that to joules, and we get something on the order of -1 times 10 to the 11th joules per mole. Just the order of magnitude of this reaction is very large compared to what you would find in a chemical reaction. And these reaction energies are so large that mass changes can be observed. And since these mass changes can be observed, as one can evaluate the Q value of a reaction, by making a balanced term, you can determine unknown masses that are produced in a reaction. Let's continue evaluating these energetics in reactions and discuss the Q value. The Q value is not necessarily equal to the energy that's necessary for the reaction to occur. Oftentimes, a reaction to proceed forward will need to overcome and be greater than the Q value. And this is because products will also have kinetic energy that need to come from the reaction. The Q value, as we'll see, is a center of mass reaction, and we need to convert this to the laboratory frame. This is due to the fact that there's conservation of momentum. The particle kinetics energy must be retained as products kinetic energy. So in other words, all the energy of the system that's defined by the Q value is not necessarily available just for the reaction. Some has to go into moving the resulting products. And the amount that's retained as kinetic energy of product is based upon the projectile mass. The retained kinetic energy becomes smaller as the target increases with the equation that's listed here, where if if I take the Q value and multiply it by the fraction of the mass of the projectile divided by the mass of the projectile plus the mass of the target, I'll get something called the equation for the kinetic energy that's necessary for the equation. We'll see this is going to eventually come into something called the threshold energy. Now let's look at this and think about what does this mean for a reaction where I have something where I'm making a compound nucleus. Let's make this a relatively straightforward reaction. Curium plus oxygen 18 going to rutherfordium 266. What does this mean if I either accelerate oxygen into a curium target or curium into an oxygen target? Well, if I accelerate the curium into an oxygen target, I use the curium as a projectile, this value, this kinetic energy, is about equal to the Q value. So we see because it's equal to 248 divided by the sum of 248 plus 18. Now if we go the other route, which is actually done experimentally, where we accelerate oxygen into curium, we wind up with only the kinetic energy being a smaller fraction of the Q value. This is one reason why you often accelerate the light particle into the heavier target. Now we can use the equations we just discussed to correctly evaluate what energies are used for a reaction to occur in the laboratory. And what we need to do, we need to consider both a laboratory and center of mass frame. For the laboratory frame, we need to consider the conservation of momentum. So in a laboratory, here's an example of a target. A projectile hits the target. We get our product and the other product from the reaction. Both the two products are moving. The particle that impinged upon the target, we can basically stay stationary. The particle moves and we have two other bodies that are moving. So we need to consider the fact that the products are moving after the reaction. They're moving at a certain energy, a certain velocity, and at a certain angle from the initial trajectory of the projectile. Now there's an equation here where we see that the Q value can be a sum of terms related to masses and the kinetic energy. So the kinetic energy of X would be the particle here. The kinetic energy of P is our projectile. And we also have information related to the kinetic energy of the product. And this allows us to consider evaluate the reaction if we know product information such as the angle in which one of the products come out of the reaction and its energy. We can find the Q value if that angle and the kinetic energy of X are measured and particles known. So if I look at this equation up here, I see that I have certain terms where the Q value is a function of different kinetic energies. This equation here relates these kinetic energies to values that can be measured, masses, and something that's known from the experiment, such as the initial kinetic energy of the particle. So if one can measure the angle and the particle kinetic energy, one can find the Q value of the reaction. Now for center of mass, where we often do equations, the total particle angular momentum is 0. In this case, it's as if the products and the reactants are hitting each other, and we get a center of mass frame that looks as shown here. We can talk about the kinetic energy from the center of mass and evaluate the two equations where we relate the kinetic energy of the center of mass and the kinetic energy of the lab, and it just winds up being equal to the kinetic energy of the center of mass is equal to the lab times a ratio of the mass of the particle and the sum of the mass of the particle and the mass of the target. The equations we just evaluated can be used to determine a threshold energy for a reaction, so the minimum energy that's necessary for the reaction to occur. We have this relationship where the Q value plus the kinetic energy of the lab minus the kinetic energy of the center of mass has to be greater than or equal to 0. We can solve for terms related to the relationship between the center of mass, kinetic energy, and the laboratory kinetic energy. So we substitute the kinetic energy of the center of mass for the laboratory kinetic energy times the ratio of the mass of the particle divided by the sum of the particle and target. We come up with the rearranged equation, which is listed here. We've put the Q value onto the other side of the equation. We take the kinetic energy of the lab term out. Now we can rearrange this equation and solve for what the kinetic energy of the laboratory must be greater than. We get to this equation here. We rearrange. We substitute the mass for A, which is a good reasonable substitution. And we come up with this very simplified equation where this threshold energy, this minimum energy for the reaction, has to be equal to the opposite of the Q value times the mass of the projectile plus mass of the target divided by the target mass. So you can use this to evaluate should we use a heavier target or a heavier projectile. And as we discussed earlier, by inspection we could see that we'd prefer to use a heavier target if possible. Using what we've just discussed, we can evaluate the threshold energy for this Rutherford reaction. Our reaction's listed here. Let's take our terms, put it into our threshold energy. Our Q value is listed here, projectile, target. This equation is transformed. The terms are listed here, and we get 1.5 MeV for the threshold energy. Now this is just the minimum energy for the reaction to occur, and it doesn't account for the Coulomb barrier. The Coulomb barrier is the charge interaction that we need to overcome to get the two particles right next to each other. The Coulomb barrier comes from the fact that I've got to take these charged particles and contact them. So the equation for the Coulomb barrier is listed here is a function of the charges, and this is our term describing the charges, divided by the radii. If we use this equation for the radii, where nuclear radii can be approximated with a constant times a to the 1/3, we can substitute this equation and show a Coulomb barrier, which is just a relationship of a constant, the z of the projectile, z of target, the a of the projectile, the a of the target. This term for since this term for the Coulomb barrier is based upon R0, you may see some variations in this equation. This equation that's listed here that we're substituting and going to put into our terms is used for an R0 of 1.5 femtometers. So we can take this term, put in our terms, the terms coming from our Rutherford reaction, where we get the z's and the a's, and we see that the Coulomb barrier is equal to 3.36 MeV. This is a center of mass equation, and we need to convert this into a laboratory frame, so we multiply the terms by the ratio of the target projectile divided by the target, and we see that what's needed in the laboratory is an alpha particle with an energy of about 4.3 MeV needed for this reaction to occur, which is what Rutherford was able to see. After discussing reaction energies, let's move and discuss how cross-sections can be utilized to evaluate the rate of formation of products from these reactions. As we discussed in the chart of the nuclides, we have data on the cross-sections, and these cross-sections are generally probabilities for reactions to occur. They have a dimension of an area, and as we read that area as 10 to the minus 24 centimeter squares. This comes from the probability of a reaction between a nucleus and a particle basically being the size of the nucleus itself, so the nucleus acts as a target. As we're going to discuss after these equations, we can have cross-sections that are much larger than this one barn. We can have cross-sections that look like 1,000 times the size of the nucleus. So this fundamental idea doesn't hold true for charged particles that have to overcome the barrier, Coulomb barrier, or for slow neutrons, in which wavelength overlap is going to have an influence on those cross-sections. And as neutrons go faster or particles go faster, we see that cross-sections tend to get towards one barn, and then if we have complicated reactions, they'll be well under a barn in some cases. So for this term, it's important to remember that one barn is 10 to the minus 24 centimeters squared, and we can use that value for performing equations and calculations on rate of formation of radionuclides in nuclear reactions. Cross-sections can be used to determine the rate of formation of the products from the reactions. There are two equations that are listed here. One is for accelerators and one is for a target in a neutron flux. So for the accelerators, we have the rate is equal to the incident number of particles per unit time, the number of nuclei per centimeter cubed, the target thickness in centimeters, so now this unit becomes centimeters squared, and then the cross-section. So these terms are related to an accelerator. If I give you an incident particle flux per unit time, that's usually a current, so that's particles per second, you can get the formation rate per second of the products from that reaction. For a target in a neutron flux or in a reactor, the equation's a little different. The rate is the same. We're looking at some process per unit time, so particles formed or atoms formed, nuclei formed per second. But the data we have is our cross-section, which we've already explored these cross-sections in the chart of the nuclides. The flux, that's how many neutrons per centimeter squared per second, and the number of nuclei that are in the target. We can get this from the mass. All right. So we have two primary equations, and we can utilize some examples, and we're going to focus primarily on the reactor examples. Now there's also something else we need to consider, is the product nuclei that's formed. If it's radioactive, we need to consider its half-life in terms of the total radiation time. If something's radioactive, as it's being made, it's also decaying, so there reaches a point where we have some saturation factor. This term here is listed as our saturation factor. That's the maximum level that can be reached. And if we know something about the activity, here are the saturation factors. This is what it looks like as a function of half-life. So this tells us something about how many half-lives we should really irradiate a sample before we start losing the benefit. If we irradiate a sample for over 5 half-lives, we've basically saturated, and we're not going to be making any more new isotope if we're irradiating for more than 5 half-lives of that isotope. If I know something like the activity at the end of a bombardment, and I divide that by my saturation factor, I can actually use it to calculate the total rate of formation of that product. So that's similar to the equations that we showed on the previous page. Let's do some calculations. Let's start off with something fairly straightforward. Let's say that the irradiation is short compared to the half-life of the product isotope we've made. And in this case, let's find the amount of iron-59 that we make from irradiating 1 gram of iron in a neutron flux of 1 times 10 to the 13th neutrons per centimeter squared per second for 1 hour. So the half-life is 44 days, and we're going to radiate for an hour. So the irradiation time is short compared to the half-life. This is our nuclear reaction. We have iron-59 adding a neutron, iron-58 plus a neutron going to iron-59. We look up the cross-section for that reaction. It's 1.3 barns, so that's 1.3 times 10 to the minus 24 centimeters squared. The number of iron-58 atoms that we said we had 1 gram of iron. Here's the molecular mass of iron. Multiply that by Avogadro's number. And this value here, that is the percentage of iron that is iron-58. So now here's our total amount of iron-58. Let's utilize this equation. Our simplified rate is equal to the flux times the number of target atoms times the cross-section. And if we do that, we just plug this in. We have about 3.9 times 10 to the 8th atoms per second in 1 hour. That would give us 1.4 times 10 to the 12th atoms produced in 1 hour. And so this does not account for the saturation factor, does not account for the decay of the iron-59. Now let's do the full expression where we utilize this equation, which accounts for the decay of the iron-59. And the terms we need here are the cross-section, the flux, the initial amount of target, the decay constants, and the total time. So we see here's the total time, 3,600 seconds. We said we're going to radiate it for 1 hour. Our decay constants, and then the other data that comes from this equation. We input those terms, we solve, and we see that the difference between the two is very small. 1.423 versus 1.422 times 10 to the 12th atoms of iron-59. So in this case, we could say that not accounting for the decay has not a big perturbation on the variations in the answers utilizing either equation. Let's take a different case where we have the half-life and the irradiation are on the same order. So let's say the amount of manganese-56 with a half-life of 2.5 hours from irradiation of 1 gram of manganese in a neutron flux, the same, for 1 hour. Okay, manganese-55 plus a neutron goes to manganese-56. That cross-section is 13.3 barns, so the cross-section is 13.3 times 10 to the minus 24 centimeters squared. Manganese-55, 100% of manganese is manganese-55, so we use this molar mass times Avogadro's number. That gives us the number of target atoms. Now let's plug this one in to our simplified equation here. We get atoms per second, 3,600 seconds in an hour. We say that we make 5.2 times 10 to the 15th atoms of the manganese-56 in 1 hour. This equation does not count for decay. Let's do the fuller equation where we do account for decay, put in all our terms, and we see that the result varies. And this makes sense because we're radiating for an hour. The half-life is 2.5 hours. During that hour of irradiation, the manganese is decaying. So in this case, we certainly need to use this equation to get a reasonable calculation for what we would actually observe. As we mentioned earlier, we can actually get the formation rate from the activity. So let's use our previous examples and use the equation that we've already discussed, where the activity divided by the saturation factor gives us the formation rate. If in our previous example we made 4.6 times 10 to the 15th atoms of manganese 56, the activity of that would be equal to lambda n. Well, we have n here. We plug in our lambda. This is our activity. We take that activity divided by the saturation factor, and we get 1.45 times 10 to the 12th atoms per second, which was equal to the rate of formation in the simplified equation. The values for cross-sections as we look in the chart of the nuclides can be well under a barn to many thousands of times a barn. So that really raises the question, how can these values be so large, particularly if we discuss a reaction in terms of a particle impinging upon something the size of the nucleus? Well, this pi r squared cross-section, which is fundamentally close to a barn, is approximated at high energy. However, the wave nature of particles has an upper limit of reaction that it can include the de Broglie wavelength. So fundamentally, this equation, pi r squared, can go to pi r plus the de Broglie wavelength squared. So the cross sections can be larger due to incoming particle wavelength. And if you think about that, the cross section values change with the function of energy of the particle. The target itself doesn't influence the variation in cross section. There are some terms that we need to think about to discuss this further. The main one is an impact parameter. Here's a picture of an impact parameter, B, which is fundamentally the target closest approach to the nucleus. So it's a term that we can evaluate and try to utilize to determine something about a reaction probability. We can evaluate the cross-section through using the impact parameter and the system angular momentum along with the de Broglie wavelength, where this impact parameter can now be replaced by this quantum term, the angular momentum, and the de Broglie wavelength, the wavelength of the particle. Now we can look at this, and the impact parameter can have any value between 0 and r. So the equation, the possible ranges are listed here, and where the orbital angular momentum is equal to 0 to b, where we can now sum all these terms from 0 to the maximum value of the orbital angular momentum. And we can see that the cross-section is now going to be based upon a summation of the system angular momentum cross-sections related to the impact parameter. And it's for this reason that nuclear reaction cross-sections can be much larger than the nuclear geometric cross-section, so the physical space. And this is really manifest by slow neutron reactions. Some of the details that we just discussed are listed here, where the cross-section for any angular momentum can be derived from this equation. And we can see that if we take this equation and expand it, this is for a given angular momentum, expand it for all the angular momentums, we can see that this equation winds up expanding into this term. And fundamentally, the cross-section now expands to the different angular momentums. And this represents a summing term, which is the reason that the cross-section can be much larger than the geometric mean. Now, one of the things that are somewhat limited in this, this is a good general trend for slow neutrons. However, there are some physical parameters in cross-sections that prevent values from, or that force values to change as a function of energy. So here's what we just discussed for the thermal neutrons. Their low energy resonances are large. These cross-sections are large. As the energies increase, the de Broglie wavelength changes. It becomes much smaller, and the cross-sections start coming towards, say, physical sizes. Now, charged particles, which are shown here, they have to overcome the Coulomb barrier, as we discussed with the threshold energies. So there are certain energies which we will not have any nuclear reactions. So those cross-sections start low, they increase, and they eventually start going towards geometric cross sections. Measurements can be performed to evaluate this change of cross-section with energy. Those are called excitation functions. And as we see here, there's some data for this is experimental. These are calculations. The experimental is for proton-induced reaction on copper-63. We see that if we hit copper-63, everything here has a proton. The products that come out could be a neutron, proton-neutron, proton-2-neutron, or 2 neutrons. So if we perform a reaction, we provide information about the products, we can get cross-sectional data by looking at the change of the product concentration as a function of energy. We can actually perform these experiments simultaneously if we have number of different targets in a system. So if I put in a number of different copper foils and I expose this to a single beam, each time that beam passes through one copper foil, it'll decrease in energy. So I can evaluate different energies and obtain data from multiple reactions at a given time. Now, if I were to go to the chart of the nuclides and look what would happen if I added a proton to copper 63 and emitted a neutron or proton and neutron or proton 2 neutrons or 2 neutrons, I would see that I would have a range of different products. We can evaluate these products through their radioactive decay, measure their rates of formation, and if we measure their rates of formation or the total amount that was formed, we can get the cross sections. So we see that we can provide that for a reaction with many different outcomes or different particles outcomes, so for instance a proton or a neutron. And here's an example of a reaction where we just get 2, 3, 4, or 5 neutrons out. Now this is experimental, this is calculated, and the reason we'd be interested in these calculations is that if we wanted to perform this experiment with calcium and berkelium, we'd want to get an idea of what energy we should perform the experiment at. And if we see we have the center of mass energy on the order of 210 will give us the 3N reaction maximum, 215 will give us the 4N reaction maximum, and we'll also get an idea of the cross-section here listed in picobarns, so you can get an idea of the rate of formation. One final detail that we'll discuss about reactions, cross-sections, before we leave this lecture is the influence of the charged particles on the barriers themselves. As we mentioned with the threshold reactions, we also need to include information about the Coulomb barrier to understand the minimum reaction energy that's necessary for a reaction to occur. Coulomb barriers can also have an influence on the excitation functions that are observed experimentally. We know that below a certain value we will not get a reaction to occur. Coulomb barriers, they'll have an influence on the minimum energy that's needed, as we discussed earlier, but the Coulomb barriers are also going to affect the charged particles exiting the nucleus, not only entering it. Charged particles emitted from nuclei experience Coulomb repulsion during emission, so they get accelerated out of the nucleus, and we'll actually observe this when we discuss or as examples with positron emission, something like copper-64 emission, which can do both positron and electron, shows the difference in the emission spectra due to this Coulomb repulsion. And this can be related to change in cross-section with energy for charged particle reaction. And as we know from our previous example on the past page, there are maximum points in which the cross-section is the greatest as a function of energy. And for experiments, if you're interested in producing the target nucleus, you'd want to perform an excitation function to determine what are the parameters to maximize production. The data is shown here. Again, as a function of energy. For one reaction, antimony and alpha 3N to make iodine, we see that reaction maximum energy around 35 MeV is needed. And the other one where we have a proton on natural zirconium to make niobium 96, we see that incident proton energy of about 8 MeV is needed. Right. This concludes the first part of this lecture. Please post any comments to the blog.